Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. I've been asked by a few students to perhaps do a practice for conceptual problems. So these are problems that don't involve calculations. I thought it was a brilliant idea. So what I decided to do is this is basically the practice. I've got 18 questions for you. It's going to be quick, and hopefully you'll have the energy to basically do these along with me as I go along. Try and pause the video, solve the problem before I reveal the answer. Okay, let's see how you go. So get a piece of paper and maybe write the answers down. See how many you get out of 18. Okay, let's go. Okay, question one. What is the definition of momentum? Momentum is, hopefully you remember this, is it a force applied over distance? Is it mass times velocity? Or is it acceleration over time? Of course, momentum is mass multiplied by velocity. And if an object has huge mass and is traveling at very big velocity, then it's going to have a very big momentum. Of course, the first one, force applied over a distance, that's actually I haven't heard of that before. Force applied over area is pressure, and then acceleration over time, that's something called jerk. Um, that's the actual term for it. No, it's mass times velocity, obviously. Okay, which of the following statements is true regarding the conservation of momentum? Momentum is always conserved in any type of collision. Momentum is only conserved in elastic collisions, or momentum is never conserved in collisions. Well, hopefully you know by now that momentum is conserved in any type of collision. So what happens there is whether the collision is elastic, perfectly elastic, inelastic, or perfectly inelastic, it is always conserved. Momentum before equals the momentum after in a closed system. Momentum before equals the momentum after as long as there is no external forces acting on the collision. So that is to say, if the two objects collide and whether they bounce off each other or whether they stick together, it doesn't matter. The momentum before will equal the momentum after. Okay? So it's conserved in any type of collision. Which of the following does not represent impulse? So we know there are kind of like two definitions for impulse. The first one is that impulse is the change in momentum. The second one is that impulse is force multiplied by time. So in this case, we have the change in momentum, which is the first one. The second one says the force applied over a period of time. So both of these are correct. This first one is correct. Second one's correct. The distance traveled by an object over a certain time. No, last time I checked, that was speed. So that's the wrong one. Let's have a look at number four. In an inelastic collision, what happens to the momentum? In an inelastic collision. So inelastic collisions are ones where the objects stick together. What happens to the momentum? Well, it doesn't actually matter. That's kind of a trick question. Whether it's inelastic or elastic, the momentum will always be the same. It will always remain constant. Okay? So it doesn't matter what kind of collision it is. It's always going to remain constant before and after. What type of collision results in objects sticking together after the collision? So in an elastic collision, what happens is that the objects bounce off each other. In a perfectly elastic collision, oh, okay. So in an elastic, they bounce off each other, but then there's some losses in kinetic energy. So first of all, they both have their own speeds. They come and they collide, and of course you hear the sound. So that means some of the energy is lost as sound, some of the energy is lost as heat, some of the energy is lost as what else could it be lost as? Thermal energy, but which is heat. In a perfectly elastic collision, there's no losses of energy. So they come in, they bounce, and they go back, and they have the same kinetic energy. So anyway, both of these do not result in the objects sticking together. In a perfectly inelastic collision, the objects come, they stick together, and they don't leave each other. So that is the one that is correct. And of course, during our physics course this year, we're only dealing with inelastic collisions. Which of the following scenarios would result in the greatest change in momentum? A small force acting over a long time, Well, first of all, before we answer the question, what is change in momentum? Of course, you should know by now that change in momentum equals impulse. So which one will result in the greatest impulse? Impulse is force multiplied by time. That's what impulse is, which is J, or if you prefer, I, impulse. Or if you prefer, we can even write delta P. All of these are impulse. So which one is it? Small force acting over a long time. Let's give it some numbers. You know what? Let's give it some numbers. Let's make long 10 seconds, and let's make small force 1 Newton. Okay? Always easier to put numbers in there. Let's make large force 10 newtons and short time 1 second. Let's make long time, as I said, 10 seconds and large force 10 newtons. So which one would result in the highest impulse, the biggest impulse? Of course, it's going to be C. A large force acting over a long time. That's going to result in the biggest impulse or the biggest change in momentum. When a ball bounces off a wall, which of the following statements is true? A ball is bouncing off a ball. The change of momentum of the ball is zero. Well, no. Think about it. Here's a wall. The ball is bouncing off the wall. Okay? So what's the first thing you notice is that there's a change in direction. If there is a change in direction, there is a change in velocity. Momentum equals mass times velocity. If there is a negative sign, then that means the velocity has changed. Okay? And so the momentum has changed. So if we say, for example, the mass of the ball is half a kilo, which is big, it's massive, or 0.1, let's make it 1/10 of a kilogram, 100 grams, and the velocity at which it's traveling is 5 meters per second, then it's going to be zero point 0.1 times 5 meters per second, which is 0.5. But on the way back is going to be zero point 0.1 times negative 5 meters per second, which is negative zero point 0.5. So the change in momentum is zero? No, there will be a change in momentum because there is a change in direction and therefore change in velocity and therefore change in momentum. The ball experiences a change in momentum due to the force exerted by the wall. This has to do with Newton's third law. For every action there is an equal and opposite reaction. The ball applies a force on the wall applies a force back, which causes a change in momentum. The third one says the ball experiences a change in momentum only. This part of the statement is true, but the only part is wrong. I mean, there is a force as well exerted by the wall. So out of those two, the second one is the most correct. Because, as I said, the ball applies a force to the wall applies a force back. This is Newton's third law. For every action, there is an equal and opposite reaction. And then, of course, there is a change in momentum because the velocity has changed the sign. Let's go to question 8. What is the unit for momentum? Is it Newton? No, that's the unit for force. Kilograms per meter? Nope. Kilogram meter per second squared? Yes, because momentum equals mass times velocity. And so what's the unit for mass? It's kg. What's the unit for velocity? It's meters per second. So that's it. That's the answer. But of course, you might also know that impulse, which is change in momentum, has a unit of ns. And so essentially speaking, that is actually the same as this. So if you write that for me in the exam, then I will mark you as correct. So yeah, just letting you know. But officially speaking, the standard international unit for momentum is kilograms dot meters per second. Okay, moving on. Which of the following statements best describes the conservation of momentum in a collision? The total momentum before and after the collision are equal, or the total momentum before the collision equals the total momentum after. That's the correct one. I don't even have to read the rest. The momentum of each object remains constant during the collision? No, of course not. The momentum of each object does not have to remain constant. But the total momentum before equals the total momentum after. But of course, those objects can slow down or speed up. One of them they can stick together. So the momentum of the objects is most likely going to change. Okay? But the total momentum of both objects together before is going to equal the total momentum of both objects after. So this is certainly wrong. Momentum is only conserved in one-dimensional collisions. No. So yes, if two objects are hitting each other like that, momentum is conserved. But also if two objects are hitting each other like that, then momentum is also conserved. And this is 2D. This is 1D. This is 2D. Okay? So it's always conserved. It doesn't matter whether it's 1D, 2D, or even 3D. It's always going to be conserved. So of course it's the first one. Next, which of the following does not represent impulse? We know impulse is equal to change in momentum. We know impulse is equal to the force multiplied by the time. Mass times velocity. No, that is in fact momentum, and sometimes momentum is equal to the impulse, but that is not the formula for impulse. Next, which of the following is an example of an elastic collision? As we said, elastic collision is one where the objects do not stick together. So the two cars colliding and sticking together, that is elastic. That is the right answer. A tennis ball bouncing off a racket. Well, bounced off, so that means it's not stuck to it. A clay ball hitting a wall and deforming. So that is also one where it is not completely. Sorry, that is, oh, it's the question is asking for elastic. So that is the elastic one. This is inelastic, and that is inelastic because obviously a clay ball hitting a wall, so I'm assuming that's going to stick to the wall. So the only one where it's actually obviously elastic is the ball bouncing off a racket. Don't worry, I'll make it more obvious in the exam if I ever bring any questions like this. Next, in a collision between two objects with different masses, which one experiences a greater change in velocity? Okay, so a really big truck, a really heavy truck, is colliding with a little tiny car. Which one's going to fly off? Of course it's the lighter one. Of course it's the lighter one. Imagine a train hitting a bicycle. Imagine a train hitting a bicycle. Now the train is very heavy. It weighs about 10,000 tons. Maybe not quite. Maybe 1,000 tons. Well, the bicycle maybe has a mass of 30 kilograms. Okay? Obviously, if a train hits a bicycle, the bicycle is going to go flying. So the lighter one is going to experience the greater change in velocity. Okay? It's a bit like saying, okay, here's an extreme example. A car is traveling on the road and it gets hit by a bug. Okay, a small tiny bug, a fly. Which one's going to experience the biggest change in velocity? The bug, obviously. The car won't even notice anything. Which of the following statements about the momentum is correct? Momentum is a vector quantity? Yes, it is. Momentum is always positive? No, because it's a vector quantity, it can be negative as well. Momentum is measured in joules? No, that's energy and work. Work is measured in joules, energy is measured in joules, momentum is measured in kilograms dot meters per second or Newton dot seconds. No, momentum is a vector quantity, the first one. Number 14 says if the momentum of an object changes, what must also change? Its mass, its velocity, its kinetic energy. Now the key word here is must. What must change? The kinetic energy does not have to change, but we're not doing kinetic energy, but these questions came from a certain place, so I couldn't get rid of everything about energy. The kinetic energy will only remain conserved in a perfectly elastic collision. But if it's a perfectly elastic collision, then that means the kinetic energy will not change. It says here must change. So let's have a look. Momentum is equal to mass times velocity. The object's mass is not going to change. What's going to change is the velocity. So if momentum changes, then most likely the velocity has changed. The object has slowed down or sped up, but the mass of the object remains the same. It's a badly worded question. I know they're looking for velocity though. Let's have a look at question 15. When the collision occurs, how are initial and final momentums related? Hopefully by now you should be able to get this one right. Initial momentum is always greater than final momentum. Final momentum is always greater than initial momentum, or is it that initial momentum equals final momentum? Of course, I think most of you know by now. Initial momentum will always equal the final momentum, and the final momentum will always equal the initial momentum. And no, not finally, we still have three more questions. What condition is required for momentum to be conserved? So it has to be a closed system, and it has to be the no net force, no outside external forces acting on the system. So objects must stick together after the collision? No. Even if they bounce off each other, momentum is still conserved. Total mass of the objects must increase after the collision? How? No. That would imply that an external force is applied. No. No external forces act on the system during the collision. That's the one. As long as no external forces are acting on the system, then you're not adding speed, you're not adding mass, so you're not adding velocity or mass, then it's going to be okay. The momentum will be conserved. Question 17 says the system is made up of two objects. If the total momentum of the system is conserved, does it mean the momentum of each object must remain the same? Remember, we kind of answered this in the beginning. Yes, momentum of each object remains constant. No, that's the whole point. If two objects collide with each other, let's say a small car and a big truck, and they stick together in a perfectly inelastic collision, then you better believe the momentum of each vehicle will change. The total momentum is the same before and after, but the momentum will change of each vehicle. Next one says no, momentum of each object can change as long as the total momentum remains constant. Of course. Third one says only if the objects have equal masses. Of course, that's wrong as well. So it's the second one. The momentum of each object can change as long as the total momentum remains constant. And finally, oh, is that question 17 again? Or do we have 19 questions? Or did I mislabel that one? Or is that question 18? No, that's question 18. So let me just change that. That is question 18. Why is it important to maximize the time over which a force is applied to reduce the impact of collision? That actually is the answer, by the way. Why is it important to maximize the time over which the force is applied? That should have been the question. The answer is to reduce the impact of collision. Okay, well, let's see the options here. To increase the change in momentum experienced by the objects involved. To decrease the impulse experience. Okay. To increase the change in momentum. What is change in momentum? Impulse. Oh, sorry. So if we maximize the time, we reduce the force. That's what happens. If we maximize the time, if we increase the time, we reduce the force. Impulse stays the same. Do we increase to increase the impulse? No, the impulse remains the same. You see, impulse is equal to force times time. If you increase this, you decrease this. This stays the same. So if you maximize the time, that's the whole point. Like if you brake, let's say for example you're in a car, right? And your father or your mother applies the brake. If they apply the brake suddenly, then that is a sudden change in momentum. The time is short, the force is very high. The change in momentum, the impulse is the same. Why is it? Because of course the momentum of the car is the mass of the people inside the car as well as the mass of the car multiplied by the velocity or the change in velocity. So let's say for example if the driver is traveling at 20 meters per second, the mass of the car is 1,000 kilograms, then it's going to be 1,000 times 10 or 10,000 kilograms dot meters per second. That is the change in momentum, that to zero. So it's going to be 10,000, right? Now whether they apply the brakes slowly or whether they apply the brakes quickly, the change of momentum is the same. The impulse is the same. You go from 10,000 to zero. That is the change in momentum, 10,000. Whether they apply the brakes slowly or whether they apply the brakes suddenly. But of course, the driver and the passengers in the car will experience two different things. Why? The force will be different. If the driver applies the brake suddenly, then the force will be huge because of this formula. If the time is less, if the time is small, 0.1 seconds, then let's say the force is going to be about 10,000, then that's going to result in a momentum of 1,000. But if they decide to apply the brake slowly, let's say for example instead they take 1 second, then the force is going to be 1,000 newtons. And now it's going to be much more comfortable for the driver and the passengers. They're not going to experience that sudden force. They're going to brake slowly. So the momentum, so the impulse doesn't change. So to increase the impulse, no. To decrease the impulse, no. To reduce the magnitude of the force, yes. That's the whole point of it. Okay? And with that, we have finished this round of revision. Best of luck. Take care.